In this video, we'll look at a very special type of series, the alternating series, which are series in which the terms, the subsequent terms, have alternating signs. So the first term might be positive, the next term will be negative, the one after that is positive, and the signs keep alternating. So let me give you this definition of an alternating series. So the series, the infinite series, that is the sum of ak with k going from 1 to infinity, is alternating if subsequent terms have different signs. This can be expressed by saying that the product of ak and ak plus 1 is negative, because if they have different signs, one of them might be positive, the other one has to be negative, so their product will be negative for all indices k. Okay, so the new term here is this term of an alternating series. So alternating series, well, we have seen some examples of them. We haven't seen any examples of alternating series. Let's see some examples of alternating series. One of them could be the series that you get by taking the harmonic series, the sum of 1 over k, and changing the signs with even k to negative. So this is 1 minus a half plus a third minus a fourth. So you see what I mean by the alternating by an alternating series. The signs keep changing each time we go to the next term. This is called the alternating harmonic series. Another example could be the sum of negative 1 to the power k divided by 2k plus 1, with k going from 0 to infinity. So this includes the reciprocals of odd numbers with alternating sign. So for the k equals 0, we get 1, then we get negative a third plus a fifth minus a seventh, and so on. Okay, so this minus 1 to the power k takes care of the sign of the sign, so it alternates. The last alternating series I want you to have as an example is minus 1 to the power k divided by k factorial, from k going to 1, going from 0 to infinity. So this is 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, and so on. Okay, so these are examples of alternating series, and there will be a special test just for alternating series, and this is our proposition. Our next proposition is the alternating series test. It's also known as the Leibniz test, which states that if you have an alternating series, the sum of ak with k going from 0 to infinity, let's say, satisfying passing the vanishing test, that is, satisfying that ak goes to 0 as k tends to infinity. So it passes the vanishing test. It might be convergent, and the additional condition is satisfied that each term in the sequence will be less than the previous one in absolute value for all indices. For all indices k, then it is convergent. So such an alternating series which passes the vanishing test and has this decreasing tendency of the terms, well, in absolute value, when you set them to be all non-negative, then it is convergent. Okay, so to prove this result, I'm just only going to give you a sketch of this proof, just to give you an idea how we might go about proving this proposition. If we look at the odd partial sums in such an alternating series, by which I mean Sm plus 1, okay, this sequence of odd indexed partial sums will be decreasing as the index increases, and even partial sums so partial sums with an even index 2m will increase. But we will also have the following inequalities for such series. So S2, the second partial sum, the sum of the first two terms, will be of course then less than or equal to then the 2mth partial sum. This is what I mean by this is also means that it's increasing. At least for these terms we have this inequality, but we can also show using this inequality here that it will be less than or equal to or even better strictly less than the m plus first partial sum, which is going to be less than or equal to the first partial sum. Okay, so this is just a1 minus a2. This is equal to just a1. So what we have here is we have the sequence of odd partial sums which are decreasing but bounded below, and we have the sequence of even partial sums which are increasing but they are bounded above. So by the monotone convergence theorem, these sequences of partial sums will be converging. The limit S2m plus 1 and S2m are convergent. One is a decreasing sequence that is bounded below, the other one is an increasing sequence that is bounded above. They are both convergent, and the limit of their difference, just to see that they do have the same limit, the difference of their limits is of course the same thing as the limit of their difference by the limit arithmetics that we have proved. But that is just the 2m plus first term in the sequence, that difference of partial sums, which by the vanishing test converges to 0 as m tends to infinity. So what we have is that this difference of limits is 0, so they agree, they are equal. This concludes the proof of the alternating series test. And to finish the video, I would like you to consider this alternating series. So apply the alternating series test to decide if it converges or not. Okay, so I want you to pause the video, think about this alternating harmonic series, and apply the alternating series test that we have just proved to that series to decide whether it's convergent. Okay, I hope you paused the video and have found that, of course, the general term in the sequence will go to 0. It satisfies the vanishing test, and each term in absolute value will be strictly less than the previous one. So each term is less than the previous one in absolute value. So it does satisfy the alternating series test. Hence, this alternating harmonic series is convergent. Okay, so unlike the harmonic series, which had all pluses, that was divergent, unlike that series, this alternating version of it is convergent. Okay, I hope you enjoyed this video, and I'll see you in the next one.